Hello, I'm Helmut Graeb from Technical University of Munich, and I'm going to present the slides for this talk. So the content of this talk is basically how to use and how to extract constraints and rules and functions from a netlist to make it usable for design. In the full talk, I will talk about how to get it from the hierarchical structure, use it for sizing, and then how to create it from the netlist plus the signal through the structure and use it for placement. This can be found in the full talk starting from slide 14 at video minute 1845. And in this short appetizer here, I will give you an example how to use constraints, rules, and functions from a large set of op-amps that have been created based on a hierarchical library, and how to use that for some simplification in sizing by using neural networks. The full version can be found on starting from slide 22. In the video, it's starting at minute 27:40. So what we have done is, or where we have started from, is that we have created a library of functional blocks. Functional blocks represent a certain analog function within a circuit. An example here is a voltage bias, which converts a current into this node in, into a voltage at the output nodes out1, or maybe there are two output nodes here. And this functional block, for instance, is a part of a current mirror. Now, a functional block can be implemented with several implementations. Here you can see some of them. So there is something special about this relation functional block, structural blocks. On the one hand, you can see that depending on the implementation, there may be additional pins, right? The number of pins of that functional block is not fixed. And then, of course, for one functional block, as you have a degree of freedom in design, there are many structural implementations. But it's also the other way around. If you have, some kind of whatever transistor pair here, this may also be part of several functional blocks. So this is a very complex relation, or it's not so easy to either analyze a netlist with regard to this, or, well, handle with the structural synthesis and all these degrees of freedom. So what we did is we took a software that, based on this functional block library, automatically created more than 500 different op-amp structures. And for each, something like more than 150 different sizings for each op-amp structure. So overall, we have something like 100,000 designs, different in sizing and different in structure. And they have been created to fill this performance space with these 4 performance features: gain, slew rate, phase margin, transit frequency, and fill the performance variable value space between the lower and the upper bound here. So in that, we have characterized all the circuits with regard to the transistor pairs, which can be identified, different current mirror types, different analog inverters at the output of the circuit, and with regard to functional blocks, which are load, transconductance, bias, and op-amp stage. And then we tried to use this to somehow simplify circuit sizing. So what we have done is we have created a neural network for each functional block over all these 150,000 designs that we have made, to map the circuit specification on the sizing of this one block, independently of all the other blocks. So we have created a neural network which has as input the functional blocks to which this current mirror belongs over all these sample elements. We have also created a reference sizing with respective performance, which we also put as an input here, and of course the circuit specification. And then in the end, if you want to design some op-amp and there is a current mirror in that, depending on the circuit specification, the neural network tells you, oh, this is the sizing of the 2 transistors that you should use. We have, here we have an example. We have a basic core of an op-amp, and you can see here now the difference between structure and function. So green is the functional block and blue is the structural block. So current mirror here is the structure, the function is bias. Down here, it's again current mirror as structure, function is load. And here you have the differential pair, the function is a transconductance. Now with these library and equations we have determined an expected sizing, which are the black values here, and also the expected performance, which is given here. And then after that, with all these kind of individual neural networks for each functional block, right, 20 and something of them, we have done the sizing, and this kind of light blue numbers here are the predicted values by the neural networks. Here it looks very good. These ones don't look that good. You can see gain is well predicted, phase margin is well predicted, transit frequency and slew rate not so well. But it's a good starting point, and this is one approach how you could use this kind of functional and structural hierarchy in a netlist, well, to help modeling in that case. So for the full presentation, please, if you're interested, take this as an appetizer and look at the complete, very long presentation.